Hello, everyone. My name is Andrea Silvestri, and on behalf of GSA's Center for Emerging Building Technologies and the GPG program, I'd like to welcome you to today's webinar on small circulator pumps with automated control. Before we get started, I want to go over a few webinar logistics. Today's webinar is based on a report by the National Renewable Energy Laboratory. You can find the full report as well as a 4-page report summary and a 1-page infographic at gsa.gov/GPG. Today's webinar will be recorded. Recordings and slides for all webinars are available on the gsa.gov website. You should also receive an email next week with a link to the recording as well as answers to some of the top Q&A. GPG webinars are presented monthly. Our upcoming November webinar will be on advanced lighting controls with LED. This report will be released shortly and provides guidance on where advanced lighting controls can be best applied. December's webinar will present findings from 3 different alternative water treatment reports that will be released in November. GPG has looked at 5 different technologies now and found that 4 out of the 5 maintained water quality while at the same time reducing water use. This webinar will discuss the findings and provide deployment recommendations. All GPG webinars offer continuing education credit. To receive credit, complete the post-webinar survey. If you do not receive a copy of the survey, please contact Michael Hobson. Today's broadcast will be listen only. You may submit questions by using the chat box on the right side of your screen. You do not need to wait until the Q&A session to submit your questions. In fact, we encourage you to submit questions throughout the presentation. Now I'd like to introduce Jay Fine, who is the project manager for the circulator pump evaluation.
All right, thanks, Andrea, and hi, everybody. Today, hopefully we're going to be able to answer all of your questions throughout the presentation and give you a lot of great information. On the screen right now, you see my contact information. So hopefully in the future, if there's an opportunity where you're looking to install one of these technologies and you're looking for some more information, I'm the one you can contact, and I'm happy to either answer your questions or I can get you in contact with the right people. Andrea, next slide, please. Okay, so today here's our agenda for this webinar. The first thing is you're going to get a 5-minute introduction from me, which I would say I've already started. When I'm done with that, you're going to hear from Jesse Dean, who's with the Department of Energy's National Renewable Energy Laboratory, or NREL, and he's going to tell you about the evaluation we did and the results of this evaluation of a small circulator pumps with automated controls. And then after that, you're going to hear from Tyler Cooper, who's with GSA's Region 8, which is in Denver, which is where this evaluation took place. And he's going to give you what we call on-the-ground feedback, which is really, if you think about it, it's kind of like the owner or user perspective on this. So he'll tell you a little bit about the installation, if there were O&M issues, and then if you were going to put one of these pumps in, kind of what you could expect. And then after that, we're going to leave plenty of time for questions and answers. And just to reiterate what Andrea already told you is that we are not going to unmute you. We do not want to hear everybody eating potato chips for 20 minutes while we're going through this. So any questions you have, you need to put them into the chat box, and we'll capture those, and then we'll go through those and present those for you. And also encourage you to put in those questions as they come up. So if you hear something and you're thinking of it, go ahead and pop it into that chat box for us. All right, next slide, please. All right, so I want to tell you a little bit about the program that I work in, which is called Emerging Building Technologies. And within that, there are 2 distinct programs. One is called GSA Proving Ground. And since that's a lot of words to say, we give it an acronym, which is GPG. And what happens in GPG is companies come up with technologies that could potentially provide some financial benefit to GSA. And those are things that that benefit comes from reduction in some type of natural resource, which is usually energy or electricity. We give that technology to GSA. We take it and we put it into a real operating GSA facility. And then we bring in the Department of Energy as kind of a third-party evaluator, and we take a look and see if that technology does provide the performance that they claim and if it could have some benefits for GSA. And so that's what you're going to hear about today, is the results of one of those GPG evaluations. The next thing that we do is called Pilot Portfolio, or P2P, and that's our group's effort to support the deployment of those proven technologies throughout GSA. To trying to get those things, and once we know that they're good and that they have value, trying to get those installed in other GSA buildings. So combining those two programs together, those are things that enable GSA to make sound investment decisions in next generation building technologies based on their real world performance. Okay, next slide, please. All right, so today you're going to hear about small circulator pumps with automated controls. So this is an evaluation that took place, as I mentioned, at the Denver Federal Center. And there were two applications of this. One is in a domestic hot water application, and the other one is in an air handler unit. And to understand the application, think about at home when you go take a shower, you turn on the water, the first thing that comes out of your shower head is cold water. And that's because the water is in the pipe that goes from your shower head all the way back to your hot water heater has to clear before you get to that hot water. If you think about what happens in a big commercial or federal building, that could be a long run from where that heat source is all the way to where the discharge is. So what typically happens is they put in a circulator line, which has hot water circulating, and that circulation takes place with a pump that moves that water through the line. Typically, those pumps are constant speed. They're just on and they run all the time. It's estimated that there's about 30 million of those types of pumps throughout the United States. And so what we evaluated was a technology that does two things to improve on that constant speed pump. One is that it has a variable speed, and the second thing is that it has sensors and logic that are built in that tell it when it should run faster, run slower, shut off, all those types of things so that it can improve the performance and the energy consumption of those pumps. Okay, next slide, please. All right, so I'm going to go ahead and turn this over to people who can tell you more about the details of what we did and what we found. So our first presenter is Jesse Dean, and as I mentioned, Jesse works for NREL. He's been there for 11 years. He has a BS in mechanical engineering from Colorado State University, and he has a master's in civil engineering from Building Systems program at the University of Colorado. And Jesse manages the support that the GSA Proving Ground gets from NREL, and he also manages support that NREL provides to a similar program at DoD called Environmental Security Technologies Certification Program, or ESTCP. On this project, Jesse was the principal investigator. So Jesse, if you go ahead and make sure that you're unmuted, I'm going to go ahead and turn this over to you.
Okay. Yeah, thank you, Jay, and thanks everyone for taking the time to join us today. Okay, next slide. So really quickly, we're going to kind of walk through the opportunity for these small circulator pumps. As Jay mentioned, there's about 30 million of them that are estimated to be in operation in the United States. The estimated energy efficiency gains from replacing those is estimated at over 50%. And I think one of the interesting notes here is that over 90% of the currently installed circulator pumps are the older constant volume pumps with standard induction motors. And we'll kind of get into the details on the next slide of what a circulator pump is. But I think at a high level, the main takeaway here is that there's a very kind of large opportunity throughout the United States. And to date, only a small number of those have been retrofitted with these high-performance circulator pumps. Okay, next slide. So a high-performance circulator pump, the definition for a circulator pump itself is essentially a small pump that has the motor rotor, the pump impeller, and the support bearings that are all sealed inside of the pump. Sometimes you're going to hear these called inline pumps, as the pump flanges are mounted directly to the piping system. As Jay noted, I think one of the big kind of technological advances or innovations with this technology is that we're moving from kind of an older, inefficient induction motor to a modern kind of ECM motor. The ECM motor itself has kind of integrated power electronics that allows integrated speed control so that the pump can ramp up and down without having to have a secondary variable frequency drive. This pump also has a number of kind of pre-programmed control modes, which you'll see there. and it has the ability to do kind of local and remote monitoring of all of the operational characteristics of the pump. So you're able to monitor things like pump power, BTUs of heat delivered, supply water temperature, pump speed. All of those things are actually built into the internals of the pump. One thing that I think is important to note is that the Energy Policy Act of 1992 kind of set the first efficiency standards for motors, but they did not apply to motors that are less than 1 horsepower. And so for a lot of these pumps, including the ones you'll see in our demonstration here, they're going to have really low kind of motor efficiencies and low power factors. And so moving to these kind of modern state-of-the-art pumps tend to have greater energy savings than you'll see in kind of larger commercial building applications. These are applied to motors that are 2.5 horsepower or smaller. This particular vendor has a number of control modes that are integrated into the pump. You'll see there's constant speed, constant pressure, proportional pressure, auto adapt, flow adapt. The one that is used for domestic hot water recirculation pumps is the constant temperature mode, where the pump has an internal temperature sensor in it, and you typically set that return water temperature set point to about 10 degrees Fahrenheit below the domestic hot water tank set point. And then the pump will essentially ramp up and down to meet that set point temperature. I would say some of the other control modes in here, like auto adapt and flow adapt, are more geared towards air handling unit applications. Okay, next slide. So just a quick comparison to standard pumps. The energy savings come from a 10 to 20% more efficient motor. You also have a more efficient pump itself, so the optimized impeller gets 10 to 15% hydraulic savings. And then really the big savings comes from the built-in control algorithm. This particular one also has a built-in nighttime setback feature. And you can see the savings estimates from the vendor is up to 65% for this particular pump. Okay, next slide. So in terms of the measurement and verification that we performed, this was at the Denver Federal Center. The first building that was installed in is building 810, where we did side-by-side testing of 2 air handling unit heating coil booster pumps. And we'll get into the details of all of these on the next few slides here. And then for building 67, we retrofitted 2 domestic hot water recirculation pumps. Okay, next slide. So this graphic is a graphic that essentially just shows you what the different kind of operating ranges are for the different models of pumps that this particular manufacturer offers. You can see, even though they're smaller 2.5 horsepower pumps, you do get, you can have a fairly large flow rate up to over 300 gallons per minute. And then you can also see on the left-hand side the head pressure that the pump is able to provide. When we started this demonstration, the smallest pump that was manufactured was the 4080 that's listed there. And then about halfway through, they re-released the 32100 and 3260 pumps. And as you'll see in the next few slides, we're testing these on kind of the smallest pumps that were available. So when we started the demo, we started with an evaluation of the 4080, and then about halfway through moved to the 32100. One thing I would note is for domestic hot water recirculation pumps, especially in high-rise buildings, you're essentially kind of pumping a small amount of fluid up to the top of a facility, and so those typically tend to be dominated with high head pressure and low flow rate. It's a very challenging point on the pump curve for these pumps to operate at. And then for things like baseboard radiant coils or air handling unit booster pumps or ground source heat pump circulators, a lot of times you're going to have kind of higher flow and lower head on those. So for example, for the AHU booster pump that we looked at, it was just a single pump on a single air handling unit coil, and it essentially just kind of boosts the flow rate through that coil from the main heating system. And so the differential pressure, head pressure that has to be offset is just the pressure from that coil. So it's the lower head pressure, higher flow application. Okay, next slide. So just quickly on the results for the domestic hot water pumps that we tested. The first one is domestic hot water pump number 1. This pump served the first floor and the cafeteria of the facility. And then domestic hot water recirculation pump number 2 served floors 2 through 8. Starting on the first table there, you'll see that the baseline pump was just a 1/4 horsepower pump. It's, you know, the smallest pump that's manufactured for these applications. It was originally retrofitted with the model 4080 pump, which the sizing isn't exactly the same, but it roughly comes out to about 0.37 horsepower. And then the duty point power is essentially what the power draw from the pump is, you know, at the peak flow rate and peak differential pressure. So one thing that's interesting that you'll see here is, you know, moving from the baseline pump to the high performance circulator pump, you were able to get over a 44% energy savings, even if the pump were to run at 100% speed all the time. So very significant energy savings for this. And you see, you know, the low wire to water efficiencies, which is just a metric of pump efficiency multiplied by motor efficiency. And again, the reason those are low is because it's, you know, higher differential pressure or higher head pressure combined with low flow rates. But we had significant increase in wired water efficiency for the 4080. About halfway through, we replaced the pump with a pump that was more directly sized to the original pump. And you can see that it almost doubled the wire to water efficiency, and we were able to get about a 72% energy savings at full load. So very significant energy savings, even if the pumps were to run at full load. Similar story for the domestic hot water pump number 2. You can see very significant duty point power reductions across the board here. The same thing with this one, where we, you know, replaced it with the model 4080 and then eventually replaced it with a smaller one there. The, you know, duty point power savings for here was 53% for the model 4080 and then 74% for the other one. So again, very significant energy savings, even if the pumps were to operate at full speed there. Okay, next slide. So this is a graph that just shows the daily average load profiles for the pumps over the monitoring period. The green line is what the baseline pump looks like. I think, you know, for any kind of constant volume air handling unit or constant volume pumping system, what you'll see is essentially there's just a flat line. As soon as the pump turns on, you know, it uses the same amount of power throughout its entire operating profile. This is one of the big reasons why it's really important to kind of move away from constant volume air handlers and constant volume pumping systems. Is there's no fluctuation in power based on the actual load of the system. So the gray lines are showing you what the pump power was for the model 4080, and then the blue line shows you what the pump power was for the 32100. Again, this is averaged over the entire monitoring period, but essentially what would happen is the pumps would ramp up in the morning to kind of heat the line. Once the line has been heated, they kind of just intermittently turn on and off, or they intermittently ramp up and down throughout the day as people are using domestic hot water. So in a domestic hot water recirculation pump application, they have the potential for very significant energy savings because they, you know, are able to run at their lowest speed until people are using the faucets and there's a demand. So as you can see, we had very significant energy savings for the domestic hot water pumps. Next slide. So the measured energy savings that we got for domestic hot water pump number 1 was 90% for the 4080 and 96% for the model 32100. For domestic hot water pump number 2, you'll see the energy savings percentages were really similar there. The total kilowatt hour of savings for domestic hot water pump number 2 were roughly twice as high as the other one. And the reason for that was the flow rate and the load that one was serving was about twice as high, because again, it was pumping, that domestic hot water fluid up to the 8th floor of the facility. But as you can see here, we had greater energy savings than we were anticipating on these, due to the pumps being more efficient and then also being able to kind of ramp down during their operating period. Okay, next slide. So this is a table that shows you what the economics look like here. So I'm just going to kind of go through these one by one. The annual energy cost savings is a combination of the energy cost savings and the estimated demand savings. They have a kind of complicated time of use rate here, so we did try to estimate, what the demand and energy savings were. Given that they operated continuously during the middle of the day, we just assumed that, the demand savings are coincident with the peak savings there. One thing to note, though, is that the annual O&M savings was $75 a year, and the on-site staff were estimating that those savings come from not having to grease the bearings or replace the pump seals. So the O&M savings for these small pumps are very significant, as much or more than the energy savings. And then we looked at the economics in terms of an end-of-life replacement. So, assuming that you have a domestic hot water pump that has failed and we're putting in a new one, these are roughly $575 more expensive than the market standard pump. So in those cases, the simple payback you can see is 3 to 4 years. So very attractive kind of payback for both applications there. Okay, next slide. So the next one that we looked at was the air handling unit evaluation. This one was different than the other one in that we tried to essentially find 2 air handling units that were as identical as possible. And so we have an air handling unit number 17 and 19 in building 810, where we did side-by-side testing. So rather than doing before and after testing, we just monitored these in parallel. There was a pretty big difference, though, in the approach. One of the things was the air handling unit 17 pump had failed prior to us starting the demo. And so we had to replace the baseline pump with kind of a modern market standard pump by Grundfos, which ended up being a lot more efficient than an older 10 to 15 year pump that you would see in that application. And so this is more of an analysis of what does a new market standard pump look like versus a new high performance circulator pump. So for air handler number 19, we put in the high performance circulator pump, and then we also closed off the bypass valve on the 3-way valve there. That bypass valve essentially for constant volume systems allows the water to bypass the heating coil when the valve starts to close down. And so you need to kind of close that for variable speed applications so that you're able to just directly modulate the flow that's going through those. Okay, next slide. So the air handling unit demonstration was a little more complicated than the other one. When we first selected these, both air handlers were operating for about 20 hours per day. But the air handling unit 19 was not meeting discharge air temperature set point, and it was not kind of responding to the control mode signals correctly. And it was determined that the facility needed to be retro-commissioned, and so they did a kind of a full retro-commissioning of the entire facility, which delayed the demo by about a year. And then after the facility was commissioned, the air handling unit number 19 was only operating very intermittently. it was serving an internal zone within the building, and so it would essentially kind of turn on for a couple hours in the morning to heat the zone up. Then the zone would switch over to cooling mode, and the pump would turn off all day, and then it would run for a couple hours at night. So it was a challenging, I think, demonstration from that perspective, because we had a number of changes that happened as we were going along here, but I think are definitely kind of good lessons learned for future projects. So the way we estimated the savings was we just, since air handling unit 17 runs at a constant power while operating, we compared its energy usage to air handler 19. Next slide. So this shows the measured energy savings from the two. I think it's important to note, if you look at the first line, the max power is just slightly lower for the high performance circulator pump. If you remember on the domestic hot water ones we went over, we saw, you know, somewhere from 44 to 73% reductions in peak power when we compared this to an older pump. When you're comparing it to a kind of new market standard pump, it's very little energy savings at peak power. I think it's only about 7%. And so really the savings that are achieved are when the pump is allowed to kind of ramp up and down to meet the load. And in this case, since the pump only ran for a few hours a day, it ran at a higher speed than the domestic hot water pumps. So you'll see that we got a 35% on-peak savings, 24% off-peak savings, with a 25.7% overall savings. Okay, next slide. So on the economics of this one, the first line just kind of walks through what the annual cost savings were. Again, they're extremely low on the energy cost savings because the pump really doesn't run much. But assuming the O&M savings for this, we still have a good simple payback. The incremental cost is also lower because for domestic hot water recirculation pump applications, you have to have a stainless steel pump. And for heating hot water, you can use a cast iron pump, so it's a cheaper pump. We did run another scenario where we were looking at what the energy savings would have been, assuming that it would have ran closer to the 20 hours a day like it did when we first looked at it. And then also assuming that the older pump that had failed was still in there. So again, I think if you're comparing this to an old market standard pump that's in the end of its lifetime, you should anticipate getting good savings. If you do have a newer pump that's just a couple of years old, again, your savings are primarily going to come down to the variable speed operation. Okay, next slide. So one of the main benefits for these pumps is they do have pre-programmed control modes that are built into them. The constant return water temperature is a nice feature where essentially you're only using the on-off from the building automation system control. We ended up using just a 0 to 10 volt control for the heating pump. The reason for that was the auto adapts mode does not work well if the pump is oversized and operating on the lower end of its pump curve. But again, you can use the internal control mode to the pump. And a big benefit from being able to do that is you don't have to add a number of points to the BAS, which can be more expensive than the pumps themselves. So having those internal control modes, I think, is very valuable and allows you to just typically use kind of an on-off or one additional point from the building automation system instead of having to add a bunch of points in. As noted before, for a standard pump, you would also have to add a variable frequency drive-in or a number of other things. So having all of this integrated into the pump provides a lot of value in terms of the cost effectiveness of it. Okay, next slide. So the lessons learned that we have, I think we covered these already. You know, for any heating or chilled water or radiant baseboard application, You do need to make sure that if they have three-way valves, that you're either converting that to a two-way valve or closing off the bypass so that it's allowed to operate as a variable flow system. And as we noted on the last one, BAS integration costs can greatly increase the overall price to the point where those could be more expensive than the pumps themselves if all the BAS points were integrated. Okay, next slide. Another important point I think that's challenging for these smaller circulator pumps is they typically don't have differential pressure points or ports. And so you're not able to actually kind of look up on the pump curve exactly where the pump is operating. And you're really just kind of looking at what size pump is currently installed. We do have a couple of approaches that could be taken to making sure that you're correctly sizing the pump. I would say for a lot of these, you're probably going to see that the existing pump is oversized, and I would work with the manufacturer to kind of help you right size that pump. So as you can see for the domestic hot water ones, even though we had good energy savings, we got better savings and better economics by right sizing those. So it is tricky with these, but just something to look at there. Okay, so I think that's all I have. Oh, no, one more. So in terms of deployment recommendations, I would say domestic hot water recirculation pumps are should be targeted with as little as 40 hours a week of operation and low electric rates. The heating and chilled water pumps, you know, you want to look at systems that operate more than 10 hours a day. Those can be challenging because if your cooling system only runs for 4 months per year, it has a lot less operation than a domestic hot water pump that's running all year long. So just kind of need to look at, you know, how many hours per year is it running. For these little pumps that serve multiple coils, you should also have better savings. So if I have a circulator pump that serves, let's say, 6 radiant baseboard heating coils, I'm going to have a larger fluctuation in flow rate, and I'm going to need to keep that pump on, you know, during the operating hours to meet those loads. And so I would look for applications where a single pump serves multiple heating or cooling coils. And then we're also estimating that the circulator pumps could be a good fit for ground source heat pump systems. Okay. All right, and with that, I'll turn it back over to GSA.
All right, great. Thanks, Jesse. All right, so let me introduce our next presenters, Tyler Cooper. Tyler's with GSA. He's in Region 8, which is Denver. Tyler's a supervisory energy project manager, and he has a degree in mechanical engineering. Tyler was on our project team from the onset, and he's what I would call the conduit kind of between the evaluation team and the local operations and maintenance staff. So he gives kind of a unique perspective of, he understands both what we were trying to do from an evaluation standpoint and also taking a look at what happened on the ground and at the location where the evaluation took place and operations and maintenance staff that was dealing with it. So Tyler's going to give you what we call on-the-ground feedback about the project. So Tyler, if you're unmuted, I'm going to go ahead and let you take it over.
Thanks, Jay. So let me go next slide. So kind of like starting off as far as the installation of these pumps goes, right away, like it's very simple installation. It's a like-for-like replacement. The pumps come with the necessary flange kits, so pretty much remove the existing pump, and then the new pumps will integrate right into the existing system, assuming you've met all your sizing constraints. Within both of our applications, we were able to use the existing BAS controls, which in this case was just the on-off signal coming from the BAS. One of the things that was convenient with these pumps is they have easily swappable communication cards. So for the purposes of this study, we used Modbus cards to send NREL the respective data that they needed for the internal pump sensors. And then once that initial data evaluation was completed with NREL, we were able to pull out those Modbus cards and then switch in new BACnet cards to allow for that integration into our BAS and pull those points out of the system. Next slide. So as Jesse kind of alluded to already, all of the pump contains all of the internal controls that are required. So you can this is kind of a representative example of that display. You can take the control mode, and then you get live feedback from the pump as to the actual power it's consuming and the differential head pressure that it's reading at the same time, as well as all the other sensors that are built into the pump. So within that, you have the ability to go through and change those control modes as necessary and kind of tune that process to your application based on what you're going to get the best performance with. One of the things that is available with these Grundfos pumps that we didn't test was a smartphone application, and this is pretty much allows you to go through and then you have remote control, but we have IT constraints with that, which is why this wasn't tested for this study. So, next slide. So kind of one thing we pointed out is with the sensors and diagnostics built into the pump, it does allow for you to go through and get real-time feedback from these pumps. So you can go through, like we kind of said, do a yearly basis with reviewing the power at this point. But you can go through and check that power usage to see if you are having any issues with your system, whether it be the domestic hot water or a different circulator application. Kind of see how those pumps are responding, if you are having any baggages or anything that would be lowering your overall system performance at that point. And then the other piece we talked about is you also have the reduced maintenance, not having to change those seals and bearings on those pumps. Next slide. So some issues we ran into during this project that just good to consider in the future. For the air handler applications, the flow direction on the pipes wasn't labeled, so when the O&M staff initially went in and installed one of the pumps, they installed the pump backwards. So that was kind of something that had to go we had to go back and rectify and make sure that was flowing correctly. The other piece that Jesse mentioned was the retro commissioning. So we had a number of points that were either programmed incorrectly in our BAS or bad sequences that were in place. So that led to incorrect operations for the system. So once we had those fixed and the entire BAS was reprogrammed, we were seeing the appropriate response from the air handlers and the circulator pumps that were going on. As far as issues with the pumps themselves, the initial 30-100 pump that we had installed, we had to replace that Modbus card in that pump. It wasn't responding correctly, giving us the data out of that. The power factor, we did see a significant improvement from the 30-100 to the 4280 pump as well, especially at lower speeds. And then kind of a thing I mentioned on the last slide is right now the mobile access to the control application isn't authorized to use IoT yet at this point. Next slide. So overall recommendation at this point is evaluating these at the end of life when we are replacing those smaller pumps and kind of looking at those runtime hours. In the case of most of these applications, we had the pumps scheduled on with the BAS already. So we're only seeing those savings during operating hours, but we are seeing increased control that we weren't getting prior to installing these pumps. Like in the case with the air handlers, because it was internal load and they were secondary pumps, the other piece we found was that the main hot water pumps from the building were able to meet a lot of that load. So it's kind of evaluating the existing conditions that you are seeing to make sure we are getting adequate runtime from the pumps when we are evaluating these opportunities. And then the other piece that Jesse mentioned is the huge, one of the huge reasons we have savings with these pumps is the varying load that exists in the building. So in the case of the domestic hot water pumps, we were able to control based on the building load, looking at the return water temperature that was being returned to the system and get real-time feedback to the pumps as far as what's going on in the building, and then subsequently able to throttle back the pumps and see those energy savings. So, And that's all I have. So with that, I'll pass it back to Jay, and then we'll start the question and answer session.
Great. Thanks, Tyler. Okay, so what I'm going to do is we've captured the questions that you guys have put into the chat box. I'm going to run through them, and we'll provide answers. Jesse and Tyler, if you just be on the ready, I'm going to need your assistance in answering some of these. So the first question was about how you get CLP or how you get continuing education unit credits for this. It's very simple. After this, if you were enrolled, you're going to get a request to do a survey. If you complete that survey, you're going to get a response that will include a certificate that shows that you attended. All right, then the next question we had was, have there been any issues with short cycling or DP spikes leading to water hammer due to speed changes that have been insufficient to accommodate dramatic fluctuations in demand? Jesse, I think you'd be a good one to take that on.
Yeah, so we didn't observe any water hammering effects with these. Yeah, I'm not sure kind of globally how big of an issue that will be, but again, they do kind of provide a minimum flow while they're operating, and then the pumps will ramp up and down to meet that flow. So I would say it's similar to, how a variable speed pump runs in a chilled water plant or a heating plant. But we didn't experience any kind of water hammering in this one.
Great, thanks, Jesse. Next question was, what does the incremental cost of the pump include? So I'm going to try to take a shot at this, and then Jesse, you can add in if I miss anything. The one is it includes the actual differential in price of the actual pump itself. The other thing that's included in that is the additional amount of time that's expected for labor to install that pump. It was estimated to be an additional 2 hours of labor, and a lot of that is not related to actually hooking up the pump itself, but there's some additional programming that had to be done on those pumps. It was also expected that 2 hours could be reduced over time because as people learn how to do that programming, the speed that can be accomplished could actually be increased, and that it may not take as much time to do that. But in terms of our analysis, we used 2 hours of additional labor. Jesse, anything besides that you want to add?
Nope, that sounds good.
Okay, great. All right, next question was, please explain or describe the domestic hot water pump control system. How is the pump controlled? Is the pump controlled by hot water use or demand and hot water recirculating temperature? Describe the demand sensors, devices, and temperature sensors that control the pump. Describe what controls the pump speed, what sensors are used to control pump speed. All right, that's a lot of stuff, but Jesse, I think you could probably tackle all that. If you need me to break it up, let me know, and I can come back and give you parts of it.
Okay. Yeah, so for the domestic hot water recirculation systems, there's a temperature sensor that's internal to the pump. And so during that setup process that Jay mentioned, essentially what the Denver Federal Center staff did was look at the domestic hot water tank set point temperature, and then program the temperature set point that's in the domestic hot water pump to be 10 degrees below that. That's kind of the industry standard rule of thumb on how to do that programming. But essentially, you're just going to determine what is an appropriate set point temperature that you want the return from the domestic hot water recirculation line to be set at. And then the pump itself just automatically ramps up and down to maintain that. So if the temperature is coming back too low, then the pump ramps up until it's able to meet that temperature, and then will ramp itself back down. So the only control that really needs to happen is the building owner inputting the return water temperature set point, and then also selecting that control mode from the pump there.
Okay, great. All right, the next question is, did the study look at the scenario where a constant speed pump was turned off at night using a simple timer? This might be a way to achieve a large portion of the savings without having to add the advanced pumps with their marginal cost. Justin, you want to tackle that one?
No, I think as Tyler said, they were already pretty aggressive in the way they were scheduling everything. The domestic hot water pumps were on a predefined building schedule. the air handling unit pumps were set up to only turn on when there was a call for a load. And so they were not on a schedule, and that's kind of why the air handling unit 19 was off most of the day. Was they already had a really aggressive schedule or a really aggressive control sequence applied to those air handler pumps to make sure they were only operating while they were running. Again, I think if it's providing heating to multiple heating coils, either air handlers or radiant baseboard heaters, you're not able to do that. You do have to keep them on a schedule. But in this case, they did that. The pump, though, does have the nighttime setback feature in it. So, you know, for some reason, if there's no connection to a building automation system, what you could do is just set up the nighttime setback internal to the pump itself, and it would turn itself off. So you could kind of do the BAS scheduling with just the pump in that case.
All right, great. Thanks, Jesse. You actually answered another question, which was, does the internal pump programming accommodate on-off scheduling for unoccupied times? So yes, you can actually do that at the pump itself. Mm-hmm. All right, the next question is, in Germany, we find usually the pumps are over-dimensioned by a factor of 2. Did you also check the dimensioning of the pumps before exchanging them? So you did address this some, Jesse, in the presentation. Is there anything else you want to add?
No, I mean, yeah, I would say that, you know, most engineers are going to be applying a safety factor to their designs, and you know, it's pretty safe to assume that they're oversized. By talking to the manufacturer, they do provide kind of on-the-ground analysis to help people size these pumps correctly. And so again, I think whichever manufacturer you're deciding to go with, I would meet with them and kind of do a run-through of your pumps and see if they can help you with the sizing. I would also say that the manufacturer provided feedback that about 50% of the time, even if the pumps are known to be oversized, the client still puts in the same size pump. So I think those were kind of some of the major lessons learned here, and we tried to do our best to address those, but is always going to be a challenge with these smaller circulator pumps.
Okay, great. How do we calculate the O&M savings? Jesse, you want to talk about that?
Yeah, we just met with Tyler's team, and they had provided guidance to us on those. So Tyler's group was the ones who kind of gave us the installation costs that we should expect from a standard pump, and then again, these are kind of site-specific O&M costs based on the O&M that Tyler's team does and the work that they were doing. So I would say that was, some of the numbers that you'll see presented in the report are very specific to the site, and could be different at different sites depending on the O&M protocols that are used. And
yeah, and I'll add on to that too. So as far as the O&M cost savings, we pretty much said that we're getting this much time savings from not having to grease those bearings, replace the seals, and then just going off of our hourly mechanic rate for that contract. And then with the installation of these pumps is the same piece, where we just went through our O&M contractor and had them complete that work, and going off that hourly mechanic rate there for the installment. So.
Okay, great, perfect. All right, the next question is, looking at the first slide of Tyler, the piping seems to be very small dimensioned for the size of the pump. It's more of a comment than a question, but Tyler or Jesse, do you have any comments or response to that?
Yeah, let me start, and then Tyler can jump in on this one. I think, again, well, I was trying to see if this was domestic hot water pump number 1 or 2. This was domestic hot water pump number 2, but we have to keep in mind that these are the smallest pumps that are manufactured for commercial building applications. You don't get any smaller than kind of 1/4 or 1/2 horsepower. And, the water lines are running in that scenario that I mentioned, where you have a very small water line very high head pressure and very low flow rate on those. So I think the reasons, the pumps look big is just because, these are kind of some of the smaller pumping applications in the buildings.
Tyler, do you have anything to add to that?
No, I think Jesse adequately covered it.
Okay, great. All right, the next question. This study appeared to look only at the electrical energy used by the pumps. Were the effects of the changing pump speed on the thermal energy studied? That's a good one for you, Jesse.
Yes, we definitely looked at that. So in the report, we have a performance criteria, or there's, what's it called? We have a performance objectives table that's in the report that outlines all the performance objectives that we wanted to hit. The performance objective related to this is essentially that the systems are able to meet the thermal loads that they're serving. And so we did install a number of additional sensors to track the return water temperature on the domestic hot water side to make sure that it was meeting that return water temperature set point. For the air handling units, our metric was ensuring that we were still able to meet the discharge air temperature set point, which was one of the drivers for the retro commissioning. Was that again, when we first got started, neither the baseline or the other pump were meeting discharge air temperature set point, and there was a number of known issues with some of the control sequences. But once the retro commissioning had happened, the pumps started responding correctly to the control mode, and they were able to meet the discharge air temperature set points. And we do have kind of those graphs, and that analysis is in the report there.
Okay, great. Next question is, what percentage of pump control and monitoring did you do directly at the pump versus in the BAS? Tyler, you want to take a shot at that one?
Yeah. So as far as the pump control for both applications, we use the command signal from the BAS as far as turning the pumps on and off and initiating that. And then the rest of the actual control mode of the pump, we relied entirely on the internal pump controls for that application. So as far as the monitoring goes, we had secondary sensors that we installed from NREL that we compared the internal sensors on the pump. And then following the completion of the study portion of the project, we were able to integrate those pumps into the BAS, and then at that point unpackage those monitoring points and not using those for control so much in the BAS, but just from the ongoing monitoring performance standpoint.
Perfect. Good answer. Thank you. All right. Just a couple more, guys. So what's a good return temp for domestic hot water? Jesse, you want to tackle that?
Yeah, I think it depends on the building and what the set point temperature is on the tank. So, for example, if your tank is heating the water to 120 degrees, the return set point is going to be somewhere in kind of the 110 to 112 or 15 range.
Great. And then the last question that we have is, how does the pump internal temperature sensor control the pump speed? Do the pump internal controls contain programming that allows the pump speed to be varied based on the domestic water return temperature? Jesse, that's probably one you could tackle.
Yeah, I mean, I'm not sure exactly the specifics of how the manufacturer is setting that up. Again, those are kind of sequences and programs that are built into the pump itself regarding kind of the ramp rate and how fast or slow it responds to those systems or to those control point changes. We didn't get in and kind of change any of that or look at that. We just kind of set the set point and then let the pump run like it normally does there.
Okay, great. Okay, so I'm going to go ahead and turn it back to Andrea. Before I do that, though, I just want to take a second and thank both Jesse and Tyler for putting together the presentation and taking the time to join us today and do this. You guys both did a fantastic job. Thank you for your help. Okay, Andrea, I'm going to turn it back to you so you can close this out.
Great. Thanks, Jay, and thanks again, Jesse and Tyler, and for all the participants for all your great questions. So as we mentioned at the beginning, you should be receiving a short survey in your email within about 15 minutes of the conclusion of this webinar, and by completing that, you can request continuing education credit. If you don't receive the survey, please reach out to Michael Hobson. And thank you again, and we look forward to seeing you at the next webinar in November. Thank you. Bye.